Hi everyone, we'll be starting class in 1 minute's time. Alright, afternoon everyone, and this week is going to be our last week for lectures in particular because we are basically on the last topic for the entire course. And this last topic is going to be based on the Z-transform, and this normally contributes towards an entire question in your final exam, which is going to be worth 20 marks out of the overall 100 marks in the final exam itself. So these lectures for this week in particular, are only going to be focused on the Z-transform. It's very important that you guys ask a lot of questions regarding what you don't understand, as well as if there's any clarity and so forth, because like I said, this is a 20-mark question out of the 100 marks in the final exam, and most of the times a lot of people make mistakes because of arithmetic errors or that they can't seem to figure out what's going to be the inverse transform and so forth. So when we read certain things and you're unsure about anything, please stop me and ask questions accordingly throughout the lecture. So the lecture today, which is going to be the first Z-transform lecture that we're dealing with, is basically going to introduce us to the Z-transform and something we're going to refer to as the region of convergence. And what we're going to see throughout the lecture is that the region of convergence basically determines the stability of our discrete time system. And what we saw so far is that for continuous time systems, the associated transform is the Laplace transform. And we also saw that there's a region for stability in the Laplace transform when we did our imaginary versus real plot accordingly. What we're going to observe is that for our discrete time systems have the Z-transform, there's also an associated region of convergence, which looks a little bit different, but we can see how the two of them will map in between the Laplace and the Z accordingly. So we need to recap a little bit here, and basically our continuous time systems that we've been dealing with so far, they have been described by differential equations. And as of such, when you're solving for those differential equations, you either do some kind of series solution, some kind of integration, or in our popular case, we use the Laplace transform and then inverse it in order to get back into the time domain. And because we're dealing with electrical and computer engineering, most of the times the Laplace transform is applied to circuits that we've been developing or trying to design. And as such, we'll get resistance, capacitances, inductances, and some sort of op-amp circuit in particular as of such. However, for discrete time cases where we have samples or instances of time which we have instantaneous values, you can't really use the Laplace transform for this because it comes like, okay, let's say we'll sample at 1 second, then that means we'll have a value at 1 second, then 2 seconds, then 3 seconds. But we have no values in between that 1 and 2 seconds and that 2 and 3 seconds. So the Laplace transform wouldn't work for this because it will be looking for a value, let's say, in between 1 and 2. That might be 1.1, 1.2, 1.3, and it just doesn't exist because it's discrete time. So as of such, when you're trying to model a discrete time case, you don't make a differential equation, you describe it by a difference equation. And the difference part of the equation is going to be the difference between two successive samples. And in describing this as a difference equation, the solution, when you solve it, is just going to be a sequence of values, which is going to be vector values in particular. That just gives us the desired response. It's possible to solve this by recursion, but it's very tedious to do so, which we saw in last week's last lecture, where we tried to do a solution by recursion, and we took out some really long summation series and so forth. So because we deal with different equations in the discrete time case, and the Laplace transform won't work with sample signals, that means we require its own individual transform in order to solve for discrete time difference equations. So some smart mathematician came up with the Z-transform for our discrete time cases, and the Z-transform, in mapping in between Z and KT, or in some cases it will be NT accordingly, was represented by this summation series equation here. And we're going to observe how we can actually apply the summation series equation in order to determine our associated Z-transforms and our region of convergence as of such. And one thing to note is that the Z-transform is actually derived from the Fourier transform because they share very similar relationships between the two of them. Now, typically, there's a one-sided and a two-sided Z-transform. The two-sided Z-transform just goes from positive infinity to negative infinity. But because we deal with causal signals, we'll be using the one-sided Z-transform throughout the entire course as of such. That means we'll be starting from k equals 0 to positive infinity instead. The right-hand side of the equation is basically the same regardless if you're using the two-sided or one-sided, just the limits change accordingly. Because this is a summation series and we have this power of z here, you'll basically see that when we expand this out, we basically get a power series and negative powers of z. And that means that, let's say we start with k equals 0, we'll be at x naught, z to the 0, so that's just going to be 1 there. And then we have x of kt, where we have k being 1, so we get x of t. And then z to the minus k will just be z to the 1, negative 1, and so forth as we keep on going. Because this is a z component, it has its own individual z plane, which we're going to see in a few slides to see what does that z plane look like. Now, because the z transform has been derived from the Fourier transform, and the Fourier transform has a similar relationship to the Laplace transform, all three of these transforms have coexistence relationships amongst each other. And it comes like when we observe the properties in between the Laplace transform and the Fourier transform, we saw a lot of similarities. We're going to see a lot of similarities with the Z transform between the two transforms as well. And as of such, it's not much things to remember. It's just going to be like similar properties and just one or two key differences that you may have to remember. So, because of the nature of the Z transform, and it shares some similarities to the Laplace transform, one such similarity is that it's possible that the Z transform of an input sequence may not exist. And this is true when the summation series converges towards a finite value, such that we do obtain a solution. But if the summation series does not converge, we will not get an associated Z transform accordingly. Thankfully, throughout this course, when we are dealing with Z transforms, all the solutions will converge to some finite value, and there will be one instance where you can actually solve an infinite solution or a non-convergent solution, which we'll discuss later on in tomorrow's lecture. So let's actually watch how can we apply that Z transform equation to some standard signals. So our first example here is the unit pulse, which is basically the discrete time version of our continuous time impulse. So we basically say x of kt is equal to 1 for k equals 0, and it's 0 for everywhere else throughout the entire thing. And if we Z transform this accordingly, that means that x of kt is 1 for k equals 0. So when k is 0 here, we have x of kt, and we just substitute that as 1, and z to the minus k here will just go 0. So that's just going to be equal to 1. But all other values of k here is just going to be 0, so that's going to be 0 multiplied by z to the minus 2, 0 multiplied by z to the minus 3 as we keep on going. So our final answer here is just going to be 1. And the region of convergence for this constant value of 1 here, that means it converges for all values of z that is possible. So this is what the discrete time unit pulse looks like graphically. So let's watch this now for the unit step. So the unit step means that for all negative values of k, it's going to be 0, but all values of k equals 0 going forward, so 0, 1, 2, 3 going all the way to positive infinity, is going to have a value of 1. If we apply this to our Z-transform, x of kt being k equals 0 going towards infinity, for x of kt here, I mean k is 0 to infinity, that just basically is going to be 1. So we'll go 1 plus z to the negative 1 plus z to the negative 2 plus z to the negative 3 and so forth as we keep on going. And we basically can see here that this summation series that we just now expanded is very similar to what we refer to as a geometric progression from mathematics. And there are some equations associated with this geometric progression that gives us the sum towards infinity for any power series expansion in particular. So for this power series that we just now expanded here for our unit step, the entire summation, when you actually apply that geometric progression formula, is that we converge this to x of z equal to 1 divided by 1 minus z to the negative 1 in the denominator. And for this geometric progression here to converge, the denominator must be more than 0. So one thing to note though is that yes, I have a modulus here for z to the negative 1 because we're dealing with the magnitude of that z value. So when you actually work in this in particular, second, I need to activate my this. I need to throw this back on for my stylus to work. Alright, good. So when you're actually dealing with the region of convergence here, and we let the denominator equals to 0, we basically say 1 minus z modulus of z to the negative 1 is going to be more than 0. So the reason why we put modulus is because the z component here is also a complex quantity, and we only care about the magnitude of that z component. So that's why we put the modulus sign in particular. So if it's going to be 1 minus z to the negative 1 here, and the modulus of that being more than 0, that means minus modulus of z to the negative 1 will be more than minus 1. And if we transform this from negative to positive, remember this more than sign here is going to flip to less than only. So that's how you get z to the minus 1, the modulus of that is going to be less than 1. So AP and GP, we're not dealing with the arithmetic progression, we're dealing with the geometric progression. And the geometric progression formula for is infinite sum starting from 0 towards infinity. That's S of infinity here is equal to A divided by R minus 1, if I believe that's the correct formula. Let me verify that really quickly. I need to verify that. So for geometric progression, the sum of infinite terms is A divided by 1 minus R, sorry. One minus R. And A here is this term. R is basically your Tn minus 1 term divided by, sorry, not your Tn minus 1 term. R is your common ratio, which is going to be T of n term divided by the Tn minus 1 term. So in this particular case, A here is going to be 1. So because that there is our first term in our entire series. And then for us to calculate for R, we can use any two successive terms. So this will be our t to the n term, so that's z to the minus 1. And this here could be our t, sorry, this is our tn minus 1 term, and this here is going to be our tn term. That comes like z to the minus 2 here, and z to the minus 1, and if you divide those accordingly, that's just going to give us z to the minus 1. And as of such, when you map the equation, you can see here that's how you get your geometric progression evaluation as of such. Right. And then there's a work in here that I explain that when you're solving for the convergence of your geometric progression, you let the denominator here be more than 0. And the reason why we take the modulus of z to the minus 1 because z here is a complex quantity and we only care about the magnitude of z. So that's why we put the modulus sign here accordingly. The work in here, it shows you how to make sure that you get positive signs for z on the outside here accordingly. And because both sides here were negative, when you multiply by negative 1, remember this 1 on side here will now flip to less than because of the change in sign accordingly. Right. You mean if it's going to be a divided by r minus 1? It'll be a divided by r minus 1 when you start changing your powers accordingly. So I'm going to show you that on the next slide in particular. So if you modify your x of z equation here to positive powers of z, that means the region of convergence is going to change accordingly. So whereas in this case we had 1 minus z to the negative 1 here is going to be more than 0. In our case, this is going to be z minus 1 here is going to be more than 0 accordingly. So as of such, because this is a positive power of z, that means the modulus of z here is just going to be more than 1. But note, in this case, this was z to the minus 1 here. So when we solve for this accordingly, because it was 1 minus z to the minus 1 here, and we did our equation manipulation and so forth, that's going to be z to the minus 1 less than 1 accordingly. T to the n and t to the n minus 1 just basically represent successive terms. So t to the n would be the highest term possible that you have here. And then t to the n minus 1 will be the term right before. So that's again z to the minus 2, and you have z to the minus 1 accordingly. And when you do the division here, that's going to be minus 2, and when you carry this on the numerator here, that's going to be plus 1. So that's again z to the minus 1 accordingly. So t to the n basically means a term that is lower down within your summation series, and the t to the n minus 1 term will be the term right before that. That's how I get the z to the minus 2 here being t to the n, and then z to the minus 1 here being t to the n minus 1. So yeah, like I was saying, if you change the powers of z throughout your x of z equation, that means your region of convergence here will change, because instead of solving for z to the minus 1, you're now solving for z. So the denominator here would still remain the same when you're calculating for the region of convergence, being z minus 1 is more than 0. But because remember z is a complex quantity, that's going to be modulus of z. So when you solve for this, because it's a positive power of z, this is going to be modulus of z being more than 1. So because it's a positive power of z here, let's actually observe what does this look like on the z plane. So the z plane, instead of using Cartesian coordinates, which we are quite accustomed to, it uses polar coordinates instead. And polar coordinates basically means that we have a circle And the radius of the circle here, r, represents our our region of convergence in particular. So all we had modulus of z here being more than 1, r here is actually 1, representing the radius of this circle. And once you have a radius of 1 and that circle exists, we refer to that circle as our unit circle. Now, because modulus of z is going to be more than 1, and we're determining a region of convergence, that means if modulus of z is more than 1, as of such, everything outside the unit circle is going to be our region of convergence. Because that's for everything for the circle being of a radius greater than 1. If for some reason our region of convergence was modulus of z being less than 1, we will shade inside that circle instead, because the region of convergence represents the area for where the radius of that circle is less than 1 accordingly. Now, when we compare this to our Laplace transform, oops, so I have a mistake here on the slide, I'll correct this accordingly. It's not going to be a half s. So, the continuous time unit step, when we're determining the region of convergence for this, that means everything on the right hand side of the S-plane will be our region of convergence for our continuous time unit step. But for a discretized time unit step, because we're dealing with polar coordinates, that means we shade everything outside the unit circle instead. So let's say, for instance, if we had a stable system here where we had the left hand side of the S-plane being shaded, where this maps to the inside of the unit circle here being shaded accordingly. So for a stable system in particular, that means, as we saw in our Rod-Hertzford criterion lecture, once the left hand side of the S-plane is occupied, meaning that all the poles are on the left hand side of the S-plane, that represents stability of our system, so that means we can shade the left hand side of the S-plane here. And to map that accordingly into our Z-plane, for a stable Z system, that means all the poles must lie within the unit circle or this radius circle here accordingly. If a pole lies on the outside of this radius circle, that means we have an unstable system accordingly. So for any stable discrete time system, basically, that means the poles of the stable discrete time system must lie within that unit circle as of such. And just to recap, our mapping, the right hand side of the S-plane basically is going to be the outside of the unit circle in the Z-plane. Conversely, the left hand side of the S-plane is going to be mapping to the inside of the unit circle in the Z-plane. So basically, if we shade the left hand side of the S-plane here, this maps to the inside of the unit circle on the Z-plane being shaded. This holds true for stable systems in the Laplace domain and the Z domain. Alright, so let's watch our third example here, where we have x of kt is equal to some constant to the power of k. And as of such, when we apply this into our x of z formula, basically that means x of kt being a equals k for k going 0 towards infinity, that a of k is going to translate here accordingly. And we have z to the minus k here, so k equals 0 is just going to be 1. But then when we go k equal 1, it's going to be a z to the minus 1. Then we have k equals 2, it's a squared, z to the minus 2, and so forth as we keep on going. If we apply this to our geometric progression formula that I wrote on a few slides before, we get our x of z here converging to the general equation here being 1 divided by 1 minus a z to the negative 1. And we can convert this from negative powers of z to positive powers of z as of such. So in determining the region of convergence here, because we have positive powers of z, that means we have minus of z here minus a needs to be more than 0. And we don't know if a here is a real quantity or a complex quantity. So for safety, we'll say minus of a. So when we transfer this across, that's going to be minus of z being more than minus of a. And the question we ask here is what's going to be our region of convergence. So the region of convergence will depend on the value of a, actually, because a represents our radius of the circle that we'll be dealing with instead. So if I extend this out accordingly for the axes, I have to excuse my crappy drawing skills there. So let's say this was the center of our axes, from here to here representing our radius of that circle. That's going to be a. And if the modulus of z here is going to be more than the modulus of a, that means we'll be shading everything outside that circle of radius a accordingly. And so long as a is less than 1 in some form or fashion for a region of convergence, that means our system will be stable accordingly. But when a is more than 1, then we have an unstable system as of such. Right. So that basically brings us to the end of today's lecture regarding the Z-transform. Okay, we have one question here. Base and power for discrete time systems will be a type of signal that you'll be dealing with only specific to discrete time systems, which is going to be like the unit step and impulse accordingly. When determining the region of convergence for these, we won't give you any sort of complex equations. We'll just tell you like, okay, it's going to be like 2 to the k or 3 to the k or something like that. It wouldn't be some weird complex equation and then you're trying to find the summation equation for the geometric progression and so forth. It'll be something simple enough for you to rectify and then just determine the region of convergence for the entire convergence equation by just equating the numerator being more than 0 and just solving accordingly as of such. So if you do encounter a region of convergence question like this, it will come like, we basically give you the equation here for x of kt, and it's going to be like some simple form of some power here, and then we ask you, okay, go ahead and expand it out accordingly and then find what's going to be our convergence equation here, and then we ask you to find what's going to be the region of convergence. So you just equate the numerator being more than 0. It helps if you transfer this into positive powers of z. It makes your life a lot easier. And once you have the region of convergence accordingly, you then need to draw your z-plane plot, show graphically what this region of convergence looks like. Good. So that basically brings us to the end of our first lecture for our Z-transform content. And basically, the important part of this lecture is just determining how do we find the region of convergence of a system if it does exist in particular. And if a question like this comes, like I just said, is we will give you the x of kt signal. You just apply the Z-transform summation equation, and then you need to apply the geometric progression equation to get it down into a simpler form. Transfer it into positive powers of z, determine the regions of convergence by letting the denominator be more than 0, and then you draw that region of convergence in your z-plane plot in particular. So are there any questions regarding the material of this lecture that need any clarification? Please ask so now. The units of the axes on the z-plane will be actually, because it's a polar coordinate plane, there isn't really a unit, so to say, because instead of it being xy coordinates, this is now r theta coordinates. So for a polar coordinate axes, the reason why I say it's r theta is because r here will represent your circle accordingly, the radius of the circle, and theta here will represent the angle from the positive axis here. So if you want to say if these were axes, this would be like a 0 degree, this would be 90 degrees, this would be 180 degrees, and this here would be 270 degrees as of such. So that would actually be your axes for this z-plane because it's polar coordinates instead of Cartesian coordinates. So it's complex it's just an angle axis, and the radius of the circle determines the magnitude as of such. Yeah, those axes are basically theta, where theta starts from the right axis, the right horizontal axis being the 0 degree line. Completely different plane. That's what we refer to as the polar plane, not the Cartesian plane. The Cartesian plane will be the xy coordinates. Polar plane is our theta coordinates. Further questions at this point? Alright, it doesn't look like we have any further questions, so if there are any further questions, feel free to leave them down in the comments below, or you can directly email me accordingly, asking those questions in particular for today's lecture. Tomorrow's lecture is going to focus on how do we actually use the Z-transform accordingly to solve for our discrete time systems, basically where we start with our difference equations and then moving towards solving those different equations using the Z-transform and the inverse Z-transform. And like I said, that topic is also quite important because that also contributes towards the 20-mark question in your final exam, and that will be one part of that 20-mark question as of such. So try your best not to miss tomorrow's lecture, and because this week is the last set of lectures, tomorrow's lecture is also going to be the last lecture for the entire course. So like I said, try your best not to miss that because that's also quite an important topic that we're going to be discussing. That's worth a lot of marks in your final exam. So until then, take care, be safe, and I will see you guys soon. Later.